Hello and welcome to part 6 of Applied Maths for Game Development. This section is on probability, and we're going to start with the definitions. So we're looking at events and outcomes first of all, and in probability, not improbability, an event is what we call something that happens and can be observed in some way. And the outcome of the event is what it results in, what happens during the event. So the set of all possible outcomes of an event is the sample space. So for example, if you have an event which is a coin toss, then the sample space is only two outcomes, heads or tails. And the actual outcome you get is whichever one of those you end up with when you actually flip the coin. But for a dice being rolled, the sample space would have six possibilities in it. Let's say you roll two dice. So here's all the possible outcomes. You could roll a 1, then another one. You could roll a 1, then a 2, a 1, then a 3, a 1, then a 4, a 1, then a 5, a 1, then a 6. And those are different outcomes from rolling a 6, then a 1, or a 5, then a 1, or a 5, a 4, and a 1, because they happen in a different order. And that can matter depending on what you're doing. So instead of one dice, which has 6 outcomes, and a second dice, which also has 6 outcomes, if you combine them both, you multiply them together and you get 36 outcomes. So that's what happens when you have multiple events. Well, assuming there's no other complicating factors, then the number of outcomes will be multiplied. So outcomes can be either favourable or unfavourable. So a favourable outcome, excuse me, is just whichever outcome you're actually looking for. It doesn't necessarily mean that it's a good event. It just means these are the things you were looking for. Whereas unfavourable outcomes are everything you're not looking for. So for example, the chance of getting heads on a coin is 1 in 2. There's 2 possibilities. Your favourable outcomes cover one of those possibilities. So there's two outcomes in the sample space, and one of them is favourable. What's the chance of getting a 6 on a 6-sided die? Well, there's 6 outcomes, and one of them is favourable, so that's 1 in 6. And if you've got 2 dice, if you want to get 5 in total out of those 2 dice, well, there's 4 ways to get that. You can roll a 1, then a 4, you can roll a 2, then a 3, you can roll a 3, then a 2, or you can roll a 4, then a 1. So that's 4 possible favourable outcomes out of 36. And you can round that down, of course. Sorry, not round that down, reduce that. Now, something called the odds. Odds are a bit different from probability, but you might not realise it at first. Now, here in the UK, odds are expressed normally as a fraction. On one side, you have the favourable outcomes, and on the other side of the fraction are the unfavourable outcomes. So, tossing a coin, the odds of getting heads are 1 to 1. But the odds of getting a 6 on a dice are 1 out of 5. Sorry, not 1 out of 5, 5 to 1 against, or 1 to 5, whichever way you want to say it. Oh, sorry, before I go ahead, that might seem a bit odd. 6 outcomes, one of them is favourable. Why is it 1 to 5? Well, because it's on the right hand side, you've got the unfavourable outcomes, so that's the chance of getting a 1, 2, 3, 4, or 5. And over here on the left is the chance of getting a 6. So that is a bit different from probabilities, which we'll see shortly. So in probabilities, we use the term P. So P is the chance of a favourable outcome expressed as a decimal, or sometimes as a percentage. So for a certain event which is guaranteed to happen, it's 100%. In other words, probability will be 1.00. Here's an example, 65% chance, it's just P equals 0.65. If you have a 3.5% chance, then P equals 0.035, and so on. Just divide it by 100. And if P equals 0, then it's an impossible event. So if you want heads on a coin, P is 0.5. If you want 6 on a dice, P is approximately 0.16666. Now, with odds and probabilities, you can convert between them. To get the odds, you take the probability and divide it by 1 minus the probability. So for example, the odds of getting heads is 0.5 divided by 1 minus 0.5. And of course, 1 minus 0.5 is also 0.5, so it's 0.5 over 0.5, or to scale that up, it's 1 to 1. That's the odds we had earlier. On a dice, the chance of getting a 6 on a 6-sided die. So a sixth is roughly 0.166. So 0.166 divided by 1 minus 0.166, or in other words, 0.166 over 0.833. That is your odds, but you can reduce that, or not reduce it, increase it rather, to 1. 1 to 5. And you can do it the other way around. You can get the probabilities by taking the odds as a fraction and dividing by the odds plus 1. So the probability of heads is 1 divided by 1 plus 1, which is 1 divided by 2, or a half. The probability of 6 on a die is a fifth divided by 1 plus a fifth, or 1.2, which gives us 0.166 in total. So they are a little bit different. They're used for different purposes. Odds obviously for gambling, so that you know who puts in the stake on either side. That's why we don't count the unfavourable outcomes among your stake. Now, among the events, some of them can be what's called independent. An event is independent if the outcome of one event does not depend on the outcome of a previous event. For example, if you flip multiple coins or throw multiple dice, each one is independent of the last one. It doesn't change it. If you rolled 3 sixes in a row, your chances of getting another 6 on the next roll, believe it or not, are unaffected. It's still 1 in 6. Now, with multiple independent events, the sample space is multiplied each time you add another event. This is kind of similar to how, if we had 2 dice, the sample space was 6 times 6. But it's not kind of similar, it's exactly that thing. So 1 dice roll, 6 outcomes. 2 dice rolls, 6 times 6, which is 36 possible outcomes. If you had 3 dice, like if you're an old school Dungeons and Dragons player, it's 6 times 6 times 6, over 200 possible outcomes, and so on. But with independent events, it becomes a bit more difficult, a bit more complex. So since the sample space is multiplied, so are the probabilities. So for example, with 1 dice, the probability of a 6 is 0.166. With a second dice roll, the probability of 6 on that dice roll is also 0.166. So with 2 combined dice rolled, the probability of getting a 6 followed by another 6 is 0.166 times 0.166, which is 0.0277. When I say more complex, it's really just more fractions to worry about, I suppose. And in case you're wondering, 0.0277 is 1 out of 36. But this is definitely more complex. Dependent events. Now, as you'd expect, that's the opposite of independent, and it means each event does depend on the outcome of a previous event. The most obvious example is a deck of cards. It's got 52 cards in it. 4 of them are aces. So on your first pull of a card, your chance of getting an ace is 4 in 52, or 7.7%. If you pick one randomly and it happens to be an ace, what's your chance of getting another one? Well, now there's 51 cards left and only 3 of them are aces. The chances change. So the next person pulling an ace, the chances are 3 out of 51, which is 5.9%. Now you can draw this instead of a table. We could do a table, I suppose. It'd be quite a large table, especially if you keep on pulling cards until the deck is done. You'd use a kind of factorial to do that, I guess. So that would be a huge table, multi-dimensional. So a lot of the times you can make a list rather than multi-dimensional tables beyond 2 dimensions. It's really hard to do, so quite often you need to do it as a list, or you can do it as a tree. So this one is just flipping a coin, so that the tree is not too complicated. The chance of getting heads on the first coin is 50%. Oh, by the way, all outcomes on this tree need to add up to 100% probability in total. For example, the chances of getting at least 1 heads on 3 separate coin flips. So you could get it on the first flip. That's a 50% chance, or 0.5 probability. The other 50% probability is you get a tails, so then you flip your second coin. You could get a heads again, 50% chance that way, or tails, 50%. And on your third flip again, 50% heads, 50% tails. But you multiply them together. So your chance of getting a heads on the first flip, 50%. Chance of getting a tail, then a heads, 50% of 50%, or 0.5 times 0.5, 25% chance. Chance of getting a heads on your third flip, 0.5 times 0.5 times 0.5, 12.5%. And finally, your chance of not getting a heads at all, 0.5 times 0.5 times 0.5, also 12.5% chance of no heads. So that's a probability tree, and they can get quite unwieldy as well. They're best used when you've got a range of possible outcomes that's not too big, but they're also quite distinct. Now all the outcomes on the right are mutually exclusive. You can't get heads on the first and second flip because you've already got one with the first flip, so you don't flip the second coin. So to calculate the total chances of exclusive events, just add the total. The chance of at least one heads is the chance of this on your first head, this on your second head, sorry, first flip, second flip, third flip. Add them all together, 50% plus 25% plus 12.5% is 87.5%. And if you've been paying attention, you may notice that's 100% minus the 12.5 unfavourable outcomes. There's not always just one unfavourable outcome here though, so be careful. You may still need to add up. So here's some rules of probability. P cannot be below 0 or above 1. Something above 100% or below 0% can exist in maths, but not in probability. And the probability of event A, outcome A is equal to 1 minus the probability of A dash. A dash is called the complement to A. It means any outcome that isn't A. So the probability of heads is 1 minus the probability of tails. The probability of rolling a 6 is 1 minus the probability of rolling a 1 to 5. Probability of pulling an ace is 1 minus the probability of pulling anything between a 1 and a 10 and a jack and a queen and a king. That's the complement. You can also see this union symbol, which is used later on, we'll see it in set theory, but it's also used here for slightly different, but broadly related purpose. So these are two exclusive events. For example, if you've got a dice and you want to find out if you can roll a 3 or a 4, then the probability of a 3 is A, the probability of a 4 is B. These are two exclusive events, and the total probability is the two of them added together. That's relatively simple, but it does add up properly. Now here is another symbol from set theory, intersection. And now this works for independent events. And for example, if you've got two separate dice and you want to roll a 6 followed by a 5, then you multiply the chances together. So your chances of a 6 go here and chances of a 5 go there. I've actually kind of seen that rule already. And this final symbol here represents the probability of A followed by B dependent on it. So what that means is we don't even check for B until A happens. And what's the chances of them both happening? And as it turns out, that's the probability of these two independent events happening divided by the probability of the second event happening. So moving on, we're going to look next at stochastic methods. Stochastic, by the way, just means randomly determined, but you don't often see it used outside of this context. So in this case, it means using randomness to find an answer to a question. And there's two main ways to go about that, or two main classes of ways to go about this. The first one's called the Monte Carlo method. We use random events to approximate an answer in a fixed amount of time. It's called Monte Carlo because it's like a gamble. You may or may not get close enough to what you want. Sometimes you can do what's called the Las Vegas method. It does really depend on what you're trying to calculate, but sometimes you can. And Las Vegas means keep on doing random events until you do get the exact answer. You're guaranteed to get an exact answer, but we're not guaranteed to say how long it's going to take to get that answer. And it's called Las Vegas because the house always wins. So we're going to look at the Monte Carlo method. It can be used for all kinds of things. For example, it's used in traffic simulation, which randomly increases and decreases, which cause traffic jams. You can simulate it and try and find the best way to route your traffic. You can predict outcomes of physical simulations, such as drug trials, or you can develop an AI for a game. It will try out random moves and develop a strategy based on what the results of those random moves are. Or procedural generation systems. It won't help with the actual generation, but it could help you figure out what's the best settings for your procedural procedures. So here's the simplest example of Monte Carlo that I can think of. Flip a coin 100 times, record how many times you get heads, divide that by 100, and that's the approximate chance of getting heads. Well, I say approximate. It's possible you could get exactly 50 out of 100, but it's more likely you'll get 49, 51, something pretty close. So it isn't guaranteed to give you the exact answer. In fact, it's quite likely to give you something that's only approximate. Let's take this to a bigger sample space. What's the chance of getting blackjack from 2 cards in a pack? Well, you could keep on dealing cards many times until you get blackjack. Well, actually, count how many times you get blackjack and divide that by how many times you've dealt the cards. And that'll give you a Monte Carlo approximation of the chances of getting blackjack. Or what's the chance of getting a certain rare drop from a rare spawn in a game? Well, keep on spawning him, killing him, getting the drop, counting how many times you get the rare one. It's probably not a terribly useful example because you probably have quite good control over your drop rates. But if it's a complicated loot table, perhaps that might be useful. Here is a concrete example, which I'm going to go over in a minute. This is a Monte Carlo approximation to find the value of pi. Now I've got the code for that here. Well, not quite the code for it. I've expanded it just slightly. So pi is what we want to find out. You know what? Actually, I'm going to load up Paint for now to show you how this works in general. So imagine you've got a circle. Now from the center to the edge, that's obviously the radius. If we make sure that radius r is exactly 1 unit, then we have a unit circle. If you could put a box around that, which I'm going to try and make it fit exactly, not quite. So if you can make a box fit exactly around that, then if the radius takes us halfway across, then the width and height of our box must be 2. What good is that? Well, our area of a box is the width times the height, 2 times 2, which is 4. The area of the circle is pi r squared. But as we've just established, r is 1, so pi times 1. Or in other words, the area of our circle will equal pi. So if the whole box is 4, and the whole circle is 3, well, pi, 3.141, we don't know that exact number, let's pretend. But the ratio of everything that falls within this box to everything that falls within that circle will be pi over 4 by definition. So all we do is we get a dartboard, we throw a nearly infinite number of darts at it. We only count the ones that land within this square. Everything over here is just ignored. And we count all the ones that fall within the circle, divide one by the other, and you get an approximation for pi. Do that enough times, and the approximation will gradually get closer and closer until you get something that's close enough for your purposes. We wouldn't actually do this in reality because there's a lot of much better ways to calculate pi, but it's just a demonstration. So we've got a diameter for our circle, we've got the center point of our circle, we've got a random number generator, we're counting how many darts fall inside the circle, and here's how many times we're going to do our dart throwing operation. So we go from 0 to that many iterations, choose a random point on the board, get the distance from there, and use Pythagoras theorem, square root of x squared plus y squared, to find the actual final distance from our dart to the center of the board. If that is less than the diameter divided by 2, then it's inside the circle. So the number of darts that are inside the circle goes up. Otherwise it doesn't. It's falling within the red area. And this line here is just going to make sure that every power of 10, or well, 5 times power of 10, it's going to draw the answer on the screen that it's got so far. And then once it's finished, it will draw that. I don't know if we'll even get that far, but we're going to give a number of items inside the circle divided by 4 times the total size of the area. That's the way to get that ratio worked out that I mentioned earlier. Okay, so our estimate of pi starts off wildly inaccurate, quickly gets a lot closer, but it doesn't really stabilize. The first digit after 3 stabilizes after about 10,000 iterations. But then the 100,000th iteration is actually further away than the 10,000th one. That's just randomness at work there, RNG being R. But after 1,000,000 iterations, we've got 3 digits stabilized, and then very quickly 4 digits. But the next digit doesn't even appear until quite a lot of steps in. So, and this is logarithmic scale as well. Well, it's logarithmic until it gets here, and then it would take too long to be logarithmic, so I skipped that. In fact, again, it jumps from being 5 digits correct back to 4, just randomness. And I'd be here all day if I waited for it to stabilize another couple of digits, because it really does take that long. But as you can see, if we only need 4 digits, 5 digits of precision, we've got there already. If you need more, you'd be here quite a while. Okay, let's take one more example. This is sort of similar. I'm not sure if it's strictly Monte Carlo, but it's certainly probability. So we're going to generate some random weapons. Imagine a kind of Borderlands type game here. So there's our RNG. We generate that many random weapons. And what we're doing is we're trying to calculate the value of the weapon, the price to the vendor. And that's based on how many upgrades that weapon has. And each upgrade is going to have a different value to the vendor. So maybe that's like just a custom grip, whereas that's a computer assisted targeting. I don't know, but each item has a different value. And then the main function just gives a wee intro telling us how many simulations it runs it, and it waits for us to press a key. I'll minimize that for now. So here's our actual simulation. We want to find out the maximum value, which is actually relatively easy because we would more or less just add up all the upgrades. But the main thing is the average value over our Monte Carlo simulation. So we do 100 million or whatever simulations in the loop. Each time you generate a weapon, and if the value of that current weapon is more than the maximum, which starts off at 0, then that's our new maximum. And then when it loops around again, we need to beat that maximum before we find another maximum. Also, we have a running total that goes up every single time. And then at the end of the loop, our final average is that running total divided by the number of simulations. Then we draw the average and the maximum to the screen. And I'm also going to put a right line at the bottom to work out the ratio between them, because these kind of analytics, what you could use them for is to say, well, if this is what a typical player gets and this is what a really lucky player could get, how would that affect the gameplay? You know, would this guy feel gypped because the other person got a much better weapon? Or, you know, we can just help to balance it a bit by looking at these values. So anyway, that's a ratio of average to maximum, but you could also draw that same ratio as a percentage by multiplying it by 100, and I'm going to do an F1 format, so it's going to be a floating point with 1 decimal place. You can also do it as a fraction. I'm not going to do a proper full-scale fraction conversion, just a really simple one where you just multiply by 10, and I'll call that tenths. So it shouldn't take too long to run compared to our pi simulation. So there we are. The average value came up as 173 credits. Maximum was 1,950. So the ratio between them is about 9%. So if you're really lucky, you'll get a gun that's worth approximately 11 times as much as the average weapon drop was, which could be valuable information for helping you analyze. And because this is random, you will get different values each time, and it's unlikely that maximum is going to change in our example because it's quite a small data set. 173.5, it's not changed that much that time. But again, that's randomness for you. Yeah, they're all relatively similar, but they are different to some extent. You can probably think of it this way. I mean, these are just a simple set of upgrades, and you pick randomly from them. That's what generate weapon did. How many upgrades does it have? Somewhere between 0 and 4. Then that many times you loop through picking an upgrade and ignoring the ones that have already been selected. So keep on choosing an upgrade until you find one that's not been selected, and then you select it. Then you add on the value of that upgrade. That's all that's going on there. But there could be a lot more complex stuff going on there. Maybe one of these has there's a subtree where if this is an underslung mount, and you might attach a shotgun or a grenade launcher, and the grenade launcher might have different ammo types, and that the exploding ammo may have chemical warheads. There could be a lot of different subtypes which all add up to very, very different values with a lot of complications. Maybe this one's not compatible with that one. This is just a really simple introduction to it, but it can get pretty complicated, and when it does, it can be really hard to analyze this without doing the kind of Monte Carlo simulation we've got here. Okay, and that's a basic introduction to probability. We'll be moving on to combinatorics next.